Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The early decades of the 20th century presented a profound challenge to the edifice of scientific knowledge. The seemingly unshakable foundations of Newtonian physics were being subtly, then dramatically, undermined by the revolutionary developments of relativity and quantum mechanics. Simultaneously, alternative epistemologies, ranging from outright skepticism to the burgeoning fields of psychoanalysis and existentialism, offered competing accounts of reality, knowledge, and the very nature of truth. It was within this intellectual maelstrom that Moritz Schlick, a man whose name would become synonymous with the Vienna Circle, embarked on a quest to establish a rigorous, empirically grounded foundation for scientific knowledge. This was the central problem that animated his philosophical endeavors. Schlick, born in Berlin in 1883, began his academic career with a focus on physics, earning a doctorate in the field in 1904. His early work, however, revealed a predisposition toward the philosophical underpinnings of science. He quickly recognized that the startling breakthroughs in physics, particularly those of Einstein, demanded a reevaluation of the fundamental assumptions about the nature of space, time, and causality. The implications extended beyond the realm of physics itself, touching upon the very possibility of objective knowledge and the validity of scientific claims. He was driven by a need to understand how science could claim to offer a reliable picture of the world, given the inherent limitations of human perception and the complexities of scientific inference. One of the initial hurdles Schlick confronted was the problem of induction. How, he wondered, could one justify the move from a finite number of observations to universal scientific laws? The empirical method, the cornerstone of scientific inquiry, seemed to provide no guarantee that future observations would confirm past patterns. This challenge, previously articulated by Hume, lay at the heart of the crisis in epistemology. Schlick understood that a satisfactory response to this problem was crucial for defending the rationality of science. He delved into the work of earlier thinkers, seeking a way to reconcile the empirical basis of scientific knowledge with the formal structure of scientific theories. Schlick's early philosophical development was significantly shaped by the positivism of Ernst Mach. Mach, a physicist and philosopher of science, advocated for a view of science that emphasized the importance of experience and the elimination of metaphysical speculation. Mach argued that scientific concepts should be understood as economical descriptions of sensory experiences, and that any attempt to go beyond these experiences was inherently meaningless. This focus on the observable and the rejection of unobservable entities resonated deeply with Schlick's own inclinations. He saw in Mach's positivism a potential framework for grounding scientific knowledge in the solid bedrock of empirical evidence. Schlick's engagement with the problem of induction and his early embrace of empiricism led him to develop his allgemeine Erkenntnislehre or general theory of knowledge. This work, published in 1918, represents a pivotal moment in his philosophical trajectory. In it, Schlick explicitly grappled with the central questions of epistemology, attempting to create a systematic account of how we acquire and justify knowledge. The book explored the relationship between experience, concepts, and the construction of scientific theories. It laid the groundwork for his later, more influential work on the philosophy of science. The allgemeine Erkenntnislehre was a response to the perceived crisis in epistemology. It also aimed to provide a clear and defensible demarcation between scientific claims and metaphysical speculation. This demarcation problem, the challenge of distinguishing between genuine scientific statements and those that are, at best, meaningless and at worst, misleading, would become a central focus of Schlick's philosophical project. Another influential figure in Schlick's intellectual development was Henri Poincaré. Poincaré, a prominent mathematician and physicist, explored the conventional nature of scientific knowledge. He argued that scientific theories, particularly in geometry and physics, often involved a degree of choice and convention. These conventions, he suggested, were not simply dictated by empirical observation, but were, in part, chosen for their convenience and explanatory power. Schlick, while agreeing with the importance of empirical evidence, recognized the force of Poincaré's arguments. He understood that scientific theories were not simply passive reflections of reality, but rather complex constructions that involved both empirical data and theoretical assumptions. Schlick's grappling with these issues, the problem of induction, the influence of Mach and Poincaré, and the need for clear demarcation between science and metaphysics, set the stage for his later, more celebrated contributions. His early work, however, already reveals his fundamental commitment to empiricism and his unwavering belief in the possibility of establishing a secure foundation for scientific knowledge. He sought to create a philosophy of science that was both rigorous and relevant, one that could withstand the challenges posed by the scientific revolutions of the early 20th century and provide a coherent account of how science works. He believed that the key to this lay in a careful analysis of the language of science and the criteria for meaningful statements. This would lead to the development of the verification principle, a concept that would define his philosophical legacy. Schlick's intellectual journey, shaped by the scientific and philosophical currents of his time, led him to a critical juncture of the demarcation problem. How does one distinguish between genuine scientific statements and those that are, at best, speculative, at worst, meaningless? This question, central to the scientific enterprise, demanded a rigorous methodology. He found a powerful tool in the burgeoning philosophy of logical positivism, and specifically in the work of Ludwig Wittgenstein. Wittgenstein's Tractatus Logico-Philosophicus published in 1921, profoundly influenced Schlick's thinking. The Tractatus offered a novel approach to understanding the relationship between language and reality, asserting that the limits of language are the limits of the world. Wittgenstein's central thesis that the meaning of a proposition is its method of verification provided the foundation for Schlick's formulation of the verification principle. This principle, in its initial conception, served as a criterion of meaningfulness. A statement, according to Schlick, is meaningful if and only if it is verifiable either through direct observation or through logical analysis that ultimately connects to observational data. This emphasis on verifiability was a direct reflection of Wittgenstein's influence, particularly his insistence that the world is the totality of facts, not of things. The facts, for Wittgenstein, were verifiable by means of the propositions that represented them. Schlick took this to mean that scientific statements, which aim to describe facts, must be verifiable. The verification principle offered a sharp tool for dissecting the claims of metaphysics. Metaphysical statements, such as assertions about the existence of a transcendent God or the nature of ultimate reality, were deemed meaningless because they lacked a method of verification. There was no conceivable observation that could confirm or falsify such claims. This stance was a radical departure from traditional philosophical approaches, which often grappled with metaphysical questions essential to their inquiry. Schlick, following Wittgenstein, prioritized the empirical and the verifiable. He sought to confine philosophy to the realm of meaningful statements, thereby eliminating pseudo-problems and clearing the way for a clear understanding of science. To illustrate the application of the verification principle, consider the statement all swans are white. This statement, though seemingly straightforward, presented a challenge. How could one verify such a universal claim? Schlick's answer, rooted in the empiricist tradition, was that the statement's meaning lay in the observations that would confirm it. One could observe individual swans and, if they were consistently white, the statement would gain support. However, the statement could never be definitively proven, since one could never observe all swans. This highlighted a crucial aspect of Schlick's early thinking, the problem of induction. While the verification principle provided a criterion for meaningfulness, it did offer a definitive solution to the problem of induction. The principle, in its initial formulation, did not claim that scientific statements were certain only that they were meaningful if they could be, in principle, verified. The verification principle's impact extended beyond its application to metaphysics. It also offered a framework for understanding the unity of science. If all meaningful statements could be ultimately reduced to observational data, then the various scientific disciplines, from physics to biology, could be seen as interconnected. Each discipline, in its own way, would be concerned with describing and explaining the observable world. This emphasis on the common ground of empirical verification provided a basis for the logical positivist project of unifying the sciences. The goal was to create a single, coherent system of knowledge grounded in observation and logical analysis. Schlick's approach to the verification principle was not merely a theoretical exercise. He was deeply concerned with the practical implications of his philosophy. He believed that a clear understanding of the nature of scientific knowledge could help to resolve many of the intellectual and social problems of his time. By clarifying the criteria for meaningful statements, he hoped to promote rational discourse and to combat the spread of pseudoscientific claims. His work, therefore, was motivated by both intellectual curiosity and a desire to contribute to a more enlightened society. The influence of Wittgenstein's Tractatus on Schlick's thought is undeniable. Wittgenstein's assertion that a proposition shows how things stand if it is true, and by saying how things stand, provided a framework for Schlick's understanding of language and meaning. Wittgenstein's emphasis on the pictorial nature of propositions, their ability to represent facts, and his insistence that the limits of language determine the limits of thought, all resonated deeply with Schlick. The Tractatus with its rigorous logical analysis, offered Schlick a model for clarifying the structure of scientific statements. Wittgenstein's idea that the world is my world suggested the importance of the observer and their experience in the construction of knowledge. Schlick adopted this focus on experience and observation as fundamental to his philosophical project. He saw in Wittgenstein's work a way to ground scientific knowledge in the realm of experience, making it both meaningful and secure. This influence is evident in Schlick's writings. He embraced Wittgenstein's emphasis on the importance of logical analysis and the need to clarify the language of science. He shared Wittgenstein's skepticism toward metaphysics and his belief that many philosophical problems were the result of linguistic confusion. While Schlick would eventually develop his own distinctive version of logical positivism, his initial formulation of the verification principle bears the clear imprint of the Tractatus. The principle's focus on verifiability, its rejection of metaphysical claims, and its emphasis on the relationship between language and the world all reflect the influence of Wittgenstein's groundbreaking work. The initial formulation of the verification principle, while offering a powerful tool for analyzing scientific statements, also faced significant challenges, which would become apparent. These challenges would necessitate further refinement and reformulation of the principle. The implications of the verification principle, however, extended far beyond the confines of the Vienna Circle and had a lasting impact on the philosophy of science. It helped to shape the debates of the 20th century and continues to influence philosophical discussions today. The initial formulation of the verification principle, despite its ambition, encountered several significant difficulties, particularly concerning the scope of its application and its capacity to account for the complexities of scientific practice. These issues centered on the verification of universal statements, the role of theoretical terms, and the inherent challenges in verifying scientific laws. The principle, as initially conceived, struggled to accommodate the nuanced relationship between theory and evidence that characterizes scientific inquiry. One of the most pressing problems concerned the verification of universal statements, those assertions that claim to hold true for all instances of a particular phenomenon. Scientific laws, for instance, often take the form of universal statements. Consider Newton's law of universal gravitation, which asserts that every particle of matter in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance separating them. The verification principle, in its early form, demanded that a statement be verifiable through direct observation. However, directly observing every instance of gravitational attraction across the entire cosmos is obviously impossible. Any attempt to verify such a law would necessitate an exhaustive survey of all particles at all times, an undertaking that is, both practically and conceptually, beyond reach. This limitation raised a fundamental question: how could scientific laws, which are typically universal in scope, be considered meaningful if they could never be definitively verified through observation? The principle, therefore, appeared to place an unrealistic burden on scientific claims, potentially rendering many of them meaningless. The very nature of scientific investigation, moreover, often involves theoretical terms and concepts that are, by their nature, not directly observable. Terms such as electron, gravitational field, or gene refer to entities and processes that cannot be perceived through the senses. While we may observe the effects of these entities, the entities themselves remain, in a sense, theoretical constructs. Consider the concept of an electron. We observe the tracks left by electrons in cloud chambers, or the behavior of electrical currents. However, the electron itself as a fundamental particle is not something we can directly see or touch. The verification principle, in its initial formulation, struggled to accommodate these theoretical terms. If the meaning of a statement is determined by its method of verification, then statements involving theoretical terms would seem to be inherently meaningless, since the terms themselves lack direct observational correlates. This would have the consequence of rendering much of scientific theorizing, particularly in physics and biology, as lacking in meaning. Further complicating matters was the Duhem-Quine thesis, a critical challenge to the verificationist program. This thesis, developed independently by Pierre Duhem and W.V.O. Quine, argued that scientific theories are not tested in isolation. Instead, they are tested as part of a larger network of assumptions, including auxiliary hypotheses, background theories, and experimental setups. When an experimental result contradicts a theoretical prediction, it is not always clear which specific component of the network is at fault. It could be the core theory, an auxiliary hypothesis, or even the way the experiment was designed. The Duhem-Quine thesis presented a profound challenge to the verification principle, because it undermined the idea that a single statement could be definitively verified or falsified through observation. Instead, the thesis suggested that scientific statements are always tested in conjunction with other statements, making it difficult to isolate the specific observational consequences of any single theoretical claim. The ramifications of this were far-reaching, suggesting that the falsification of a theory did not necessarily mean the theory was wrong, just that something in the entire network of assumptions was incorrect. This thesis, in turn, has a direct impact on the scientific method, which, at its core, relies on the testing of hypotheses. The scientific method involves formulating a hypothesis, designing an experiment to test the hypothesis, and then analyzing the results to determine whether the hypothesis is supported or refuted. However, the Duhem-Quine thesis implies that the results of an experiment never provide definitive proof for or against a single hypothesis. Instead, the results only provide evidence that either supports or contradicts the entire network of assumptions. This means that scientists are not simply testing a hypothesis. They are, in effect, testing a complex system of interconnected ideas. This complexity makes it difficult to decide which assumptions to revise when an experiment yields unexpected results. The initial formulation of the verification principle struggled to account for the underdetermination of theory by evidence. This concept highlights the fact that a given set of observational data can often be explained by multiple competing theories. Consider the historical example of heliocentric and geocentric models of the solar system. Both models could, at least in the early stages, account for the observed movements of the planets. The geocentric model, with the addition of epicycles and deference, could accurately predict planetary positions. The heliocentric model, on the other hand, offered a simpler, more elegant explanation. The verification principle, in its initial form, provided little guidance in choosing between these competing theories. If both theories were consistent with the available evidence, and if the meaning of a statement was determined by its method of verification, then both theories would appear to be equally meaningful, even if they offered radically different accounts of the universe. This underdetermination of theory by evidence posed a significant challenge to the verification principle's claim that meaningful statements are those that can be empirically verified. The difficulties inherent in defining observation also presented challenges to the verification principle. What constitutes a direct observation? Is it limited to sensory experience, or does it include the use of scientific instruments? If we consider the use of instruments, such as telescopes or microscopes, the line between observation and inference becomes blurred. When we look through a telescope and observe a distant galaxy, are we directly observing the galaxy, or are we interpreting the data provided by the instrument? The interpretation of data from instruments invariably involves theoretical assumptions. For instance, when interpreting the readings on a Geiger counter, we must rely on our understanding of nuclear physics. The verification principle, in its early form, provided little guidance on how to distinguish between genuine observations and theoretical interpretations. The very notion of observation was, therefore, more complex than the principle initially acknowledged. These criticisms of the early verification principle had a profound impact on the subsequent development of philosophical thought, particularly on the work of W.V.O. Quine, a student of Rudolf Carnap, initially embraced the logical positivist program, but he later became one of its most influential critics. To his work, Quine developed a critique of the analytic-synthetic distinction, the cornerstone of logical positivism. This distinction, which was central to the verification principle, held that statements could be divided into two categories: analytic statements, which are true by definition and can be verified through logical analysis, and synthetic statements, which are true by virtue of the way the world is and can be verified through empirical observation. Quine, however, argued that the distinction between analytic and synthetic statements was untenable. He contended that all statements, even those that appear to be analytic, are in some way dependent on empirical facts. Quine's argument, which was presented in his seminal paper Two Dogmas of Empiricism, challenged the fundamental assumptions of the verification principle. His work played a crucial role in the decline of logical positivism as a dominant philosophical movement. Quine's rejection of the analytic-synthetic distinction, coupled with his embrace of the Duhem-Quine thesis, led him to reject the logical positivist program's emphasis on the reduction of all knowledge to basic, observable facts. Instead, Quine argued for a more holistic view of knowledge, where all statements are interconnected and subject to revision in light of new evidence. His work, which emphasized the interconnectedness of all scientific knowledge, had a lasting impact on the philosophy of science. He advocated for a naturalistic approach to epistemology, arguing that philosophical questions should be addressed using the methods of science. Quine's contributions helped to pave the way for new approaches to understanding the nature of knowledge and the relationship between language and the world. His critique of the verification principle and his subsequent development of his own philosophical views marked a significant turning point in the history of 20th century philosophy. Having explored the initial formulation of the verification principle and its subsequent reception, it is now essential to examine Moritz Schlick's evolving responses to the criticisms that arose. The verification principle, in its original form, presented significant challenges. The requirement that all meaningful statements be verifiable, either directly or indirectly, through sense experience, proved difficult to sustain. Many statements central to scientific discourse, particularly those involving theoretical entities or universal generalizations, seemed to defy straightforward verification. Schlick, recognizing these difficulties, embarked on a process of refinement seeking to salvage the core tenets of empiricism while addressing the complexities of scientific practice. One of the most significant shifts in Schlick's thinking involved a move towards a more liberal understanding of verification. He began to emphasize the concept of confirmation as a crucial element of scientific reasoning. Instead of requiring complete and conclusive verification, Schlick argued that scientific statements could be considered meaningful if they were capable of being confirmed by empirical evidence. This shift allowed for the inclusion of theoretical statements that, while perhaps impossible to verify definitively, could nonetheless be supported by observational data. This move was a direct response to the inability of the strict verification principle to accommodate the probabilistic nature of scientific evidence. This transition towards confirmation was profoundly influenced by the work of Rudolf Carnap. Carnap, a fellow member of the Vienna Circle, was developing a sophisticated logical framework for analyzing scientific language. Carnap's work on confirmation theory provided a formal apparatus for assessing the degree to which evidence supports a given hypothesis. He introduced the concept of degree of confirmation a numerical measure of the extent to which evidence increases the probability of a hypothesis being true. Schlick found in Carnap's approach a powerful tool for incorporating probabilistic reasoning into his epistemology. The focus shifted from seeking absolute certainty to evaluating the degree of support that empirical evidence provides for scientific claims. Schlick embraced the idea that scientific statements, even those concerning unobservable entities, could be assigned a degree of confirmation based on the available evidence. This perspective acknowledged that scientific knowledge is inherently fallible and that scientific claims are always subject to revision in light of new evidence. This probabilistic turn, inspired by Carnap, allowed Schlick to accommodate the inherent uncertainty that pervades scientific inquiry. For example, the statement all swans are white could never be definitively verified, as one would need to observe every swan throughout all of time. However, the statement could be confirmed by observing many white swans and finding no counter-reasons. The more white swans observed, the higher the degree of confirmation for the hypothesis. Closely related to this shift was Schlick's evolving understanding of the nature of meaning. The initial formulation of the verification principle had suggested a straightforward connection between meaning and verification. A statement's meaning was determined by the conditions under which it could be verified. However, as Schlick grappled with the complexities of scientific language, he moved towards a more nuanced account of meaning. He began to recognize that the meaning of a scientific statement is often intertwined with its role within a broader theoretical framework. The meaning of a term like electron, for instance, is not simply reducible to direct observations. It is also determined by its relationships to other theoretical concepts, such as charge, mass, and the laws of electromagnetism. Schlick's work on the nature of causality further exemplifies his attempts to reconcile empiricism with the use of theoretical concepts in science. He understood that causal relationships form a cornerstone of scientific explanation. He recognized that the concept of causality, while seemingly straightforward, presents significant philosophical challenges. The Humean critique of causality, which questioned the logical necessity of causal connections, posed a direct challenge to the logical positivists' project of grounding scientific knowledge in empirical observation. Schlick sought to defend a version of causality that was compatible with his empiricist commitments. He argued that causal statements, while not directly verifiable in the same way as observational statements, could be confirmed through repeated observations and the establishment of regularities. The influence of Karl Hempel is also evident in Schlick's later work. Hempel, another prominent figure in the Vienna Circle, developed a sophisticated account of scientific explanation based on the idea of covering laws. Hempel argued that scientific explanations involve subsuming particular events under general laws. This framework provided a way to understand how theoretical concepts, such as those found in physics, could play a crucial role in scientific explanations. Schlick, recognizing the importance of explanation in scientific practice, incorporated elements of Hempel's approach into his own philosophical framework. Schlick's modifications to the verification principle had a significant influence on subsequent developments in the philosophy of science. His emphasis on confirmation and probabilistic reasoning paved the way for the development of Bayesian epistemology, which uses a mathematical framework of probability theory to model belief. Revision in light of new evidence offers a powerful tool for understanding how scientists reason and how scientific knowledge evolves. The Bayesian approach, which assigns degrees of belief to hypotheses and updates these beliefs based on evidence, mirrors Schlick's move towards a more nuanced understanding of verification. His work provided a crucial stepping stone towards a more sophisticated understanding of the relationship between evidence, theory, and meaning in science. Schlick's efforts to refine the verification principle, particularly his focus on confirmation and probabilistic reasoning, represent a significant contribution to the philosophy of science. He recognized the limitations of the original formulation and sought to develop a more flexible and nuanced approach that could better accommodate the complexities of scientific practice. His work on the nature of meaning, causality, and scientific explanation continues to be relevant to contemporary debates in epistemology and the philosophy of science. His attempt to reconcile empiricism with the use of theoretical concepts and his embrace of probabilistic reasoning laid the groundwork for many of the most important developments in the philosophy of science during the 20th century and beyond. The enduring legacy of Moritz Schlick resides not merely in the specific tenets he advanced, but in the profound shift he catalyzed within philosophical inquiry. His meticulous examination of language, meaning, and scientific method reshaped the landscape of 20th century thought, leaving an indelible mark on how we understand knowledge itself. While the Vienna Circle, with its collective spirit, often overshadows individual contributions, Schlick's role as the intellectual anchor and guiding force remains paramount. His dedication to clarity, his rigorous pursuit of logical precision, and his unwavering commitment to empirical verification provided the framework upon which the logical positivists built their influential philosophical edifice. Schlick's influence extended beyond the immediate circle of his collaborators. The impact of his work resonated with philosophers across the globe, shaping the development of analytic philosophy and influencing debates in diverse fields from ethics to the social sciences. His emphasis on the importance of empirical evidence and a critical analysis of language provided a potent antidote to the speculative metaphysics that had dominated much of 19th century philosophy. This emphasis on the tangible, the observable, and the testable directly influenced thinkers like A.J. IA, whose popularization of logical positivism in English-speaking countries brought Schlick's ideas to a wider audience. Ayer's Language, Truth, and Logic *, a seminal work that popularized the verification principle, bears the clear imprint of Schlick's guidance and intellectual leadership. The book, a cornerstone of the movement, served to disseminate Schlick's ideas, including the rejection of metaphysical statements as meaningless and the focus on the logical analysis of scientific language. The refinement of the verification principle, a central focus of Schlick's later work, demonstrates his intellectual flexibility and his willingness to adapt his ideas in the face of critical challenges. He recognized that the initial formulation, which demanded complete verification of statements, proved too restricted to accommodate the complexities of scientific practice. The probabilistic nature of scientific confirmation, the reliance on theoretical constructs, and the inherent limitations of observational methods all demanded a more nuanced approach. This led him to develop a more sophisticated account of verification, one that embraced the concept of confirmation and acknowledged the role of probability in scientific reasoning. This shift from strict verification to confirmation represented a crucial step toward a more realistic and defensible epistemology. It allowed for the acceptance of scientific statements even when complete verification proved impossible. The impact of Schlick's philosophical explorations can be seen in the development of various philosophical schools. His emphasis on the importance of logical analysis and the critical examination of language paved the way for the rise of ordinary language philosophy, which sought to understand philosophical problems by analyzing the ways in which language is used in everyday contexts. Thinkers like Ludwig Wittgenstein, whose early work profoundly influenced the Vienna Circle, and later J. Austin, whose work focused on the performative aspects of language, were, in a sense, wrestling with the implications of Schlick's insights. Although Wittgenstein later moved away from some of the core tenets of logical positivism, his initial work, the Tractatus Logico-Philosophicus share the same fundamental concerns about the relationship between language and reality, and the importance of logical structure, the search for clarity, the commitment to empirical verification, and the focus on language as the key to understanding the world all echo Schlick's influence. A critical assessment of Schlick's work reveals both its strengths and its limitations. His emphasis on clarity and logical rigor was a valuable corrective to the often vague and speculative nature of earlier philosophical traditions. His focus on the importance of empirical evidence and the scientific method helped to elevate the status of science and to establish philosophy as a discipline that could engage with the findings of the natural sciences. However, his commitment to a strict form of empiricism also presented challenges. The verification principle, even in its refined form, faced difficulties in accounting for the role of theoretical concepts in science, the challenge to provide a clear, unambiguous basis for scientific statements, and the difficulties in verifying theoretical claims exposed inherent limitations. The historical context of Schlick's work is crucial to understanding its impact. The rise of logical positivism coincided with a period of great intellectual ferment, marked by the development of new scientific theories such as relativity and quantum mechanics, and by growing awareness of the limitations of traditional philosophical approaches. The Vienna Circle, with Schlick at its center, provided a forum for discussing these developments and for developing a new philosophy that could engage with the challenges of the modern world. This intellectual environment, characterized by belief in the power of science and a commitment to logical analysis, facilitated the rapid spread of Schlick's ideas. Despite its limitations, Schlick's work continues to resonate with contemporary philosophical debates. His questions about the nature of science, the relationship between language and the world, and the meaning of meaning remain central concerns for philosophers working in epistemology, the philosophy of language, and the philosophy of science. The ongoing debates about the role of evidence, the nature of scientific explanation, and the status of theoretical concepts all bear the imprint of Schlick's pioneering work. The challenges he posed to traditional philosophical approaches and the solutions he offered continue to shape the way we think about knowledge, meaning, and the nature of reality. The enduring value of Schlick's contributions lies, ultimately, in his unwavering commitment to clarity, rigor, and the pursuit of truth. His ability to synthesize complex ideas, to articulate them with precision, and to subject them to rigorous logical analysis served as a model for generations of philosophers. His work stands as a testament to the power of philosophical inquiry to illuminate the fundamental questions that shape our understanding of the world. His intellectual honesty, his willingness to question assumptions, and his dedication to empirical evidence continue to inspire and challenge us to strive for a deeper understanding of ourselves and the world around us. The legacy of Moritz Schlick is a call to intellectual vigilance, a reminder of the importance of critical thinking, and an enduring testament to the power of philosophical inquiry.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.